All right, so today's lesson is going to be on determining the wave speed. So what do we already know about speed? Well, we know the equation. We know that speed requires a distance and a time measurement. So how does this relate to distance and a time for a wave? Well, we spoke about a specific distance or length. So when we talk about distance, we want to talk about wavelength, lambda. When we talk about time, there was a specific time for a wavelength, okay? And that was the period, or we actually spoke about frequency. Frequency had to do with number of cycles per time in seconds. But if we flip that over, we get the time for one cycle, and that's called the period. It's a special measurement of time. So it's the time for one cycle. And one cycle is a wavelength in this case. That's not division, it's just meant to mean cycle or wavelength. All right, so how do we get the universal wave equation? Well, here's speed, distance over time. So our distance measurement is really our wavelength, and our time measurement is the period, or the time to make one wavelength, to produce one wavelength. But we know this thing about frequency. The other day we talked about frequency, number of cycles per time. Well, I want to show you the relationship between frequency and period. If frequency is the number of cycles per time, period is the time. Okay, if we did a whole bunch of cycles, and that's per cycle. So if you see the relationship between these two, number of cycles, or this could be number of cycles here, they're actually the inverse of each other. So when you see the wave equation, you don't see it usually with period, you see it with frequency. So what I want you to realize is that the period is actually the inverse of frequency. So 1 over t is frequency, or period equals 1 over frequency. They're the inverse of each other. So usually how you see the universal wave equation, if I factor out just so you can see, this is actually like multiplying lambda by 1 over t, which is period. I know it's a capital T, it's not temperature, it's a special unit of time. This 1 over is actually frequency. So the universal wave equation looks like this. Speed equals f lambda, or frequency times wavelength for the specific wave. So this is frequency, and that's in hertz, which is per second, and lambda is the wavelength in meters. And if hertz is per second, then speed will be meters per second, because hertz is 1 over seconds. All right, so we'll do some examples with that. So if you want to take a second and pause there to copy that out if you're listening. All right, so on to our examples. Just get it into, here we go. All right, so imagine you're sitting on the dock after your exams. You just can't stop thinking about physics. So you want to just determine the speed of a water wave. So you're sitting on a dock, okay? And the waves, water waves, are coming past you. So what you notice is you count 15 crests going past you in 1 minute. All right? And then you also make a note of the distance between the top of the crest is 6.5 meters. So when you're doing this question, you have to think, well, if I want to find the speed of a wave, then the information given me should be able to help me figure out the frequency and the wavelength. So if the distance between crests is 6.5 meters, think about what that gives you. I'll pause for a moment. And if you need to go back in your notes, but that is the wavelength. So the wavelength is 6.5 meters because it's the distance between successive crests, which means the crest right beside it. All right. Now the other information, you count 15 crests in 1 minute. Well, that gives you something about frequency because it's telling you the number of cycles in a given time. So the frequency is number of cycles per time, and we usually want this in seconds, all right? And we're given it in minutes. So it's 15 cycles. You don't need to really write any units, it's 15, and that's 60 seconds. So that comes out to be 0.5 hertz. All right, now we're going to put that into our universal wave equation. So frequency is 0.5 hertz, and lambda is 6.5 meters. So we were just dividing 6.5 by 2. So that's going to be 3.25, and this means per second. So it's meters per second. This is a count, so it's infinitely significant. This is 2 significant figures. This is 2 significant figures. So I can only have 2 significant figures. When you use 5 to round, we round to the even. So the speed is approximately 3.2 meters per second. And this is a speed, so I don't need direction. All right, now we'll go to the next one. While swimming in the ocean, you are at the top of a crest, and your friend is at the bottom of a trough with another crest between the two of you. If you count 15 seconds while you bob 10 times, determine the speed of the waves. So if I draw a picture about what's actually happening, I'll draw a couple waves. Okay. You are here. It says you are at the top of a crest, but your friend is at the bottom of a trough with a crest between the two of you. So there's a crest, there's a trough, and it says he's at the bottom of a trough. Okay, so this is your friend. I'm going to put an F for friend. So now, do we know the distance between us? This is something I usually ask in class. So I will choose a distance, and I'm going to say you are 12 meters apart. Okay? So I don't know if you can tell by looking at this, but that's going to give you your wavelength. But it's not a whole wavelength. All right? It's actually, if I divide it here, that's a half, that's a half, that's a half, or that's 1.5. So 12 meters actually equals 1.5 lambdas. So you need to solve for lambda. To solve for lambda, you divide by 1.5. Okay, if you need your calculator, you go ahead and do that. Or maybe you can think about that in your head. Okay, and you can figure that out. Now, the second part here, when you're counting 15 seconds, you bob 10 times, that's going to give you frequency. So you count 15 seconds. So remember, it's cycles per time. So you bob 10 times, it's 10 cycles, and you have 15 seconds. All right? Now, if you want to reduce that, you can. That's going to be 2/3, and that's going to be hertz. Have you figured out what 12 divided by 1.5? Or you multiply by 2 and divide by 3 because it's actually, 3 halves. Yep, so 24 divided by 3, it should be 8 meters. Okay, because it's 4, 4, 4, right? 4, 8, 12. That's another way to do it if you want. However you do it's fine. Just show your thinking. All right, so now our equation is V equals F lambda, because now we've found lambda, we've found frequency, we can put them together. The frequency is 2/3 hertz. Lambda is 8 meters. All right, so it's going to be 16 divided by 3. Okay, and that's going to be 5.333 repeated. And that's going to be meters per second. All right. So the speed of the waves approximately, I'm going to go back here and look. This is a count. So I have 15 seconds. I gave you 12 meters here. Two significant figures. It's going to be approximately 5.3 meters per second. All right. So there's two examples of using that. Now, you should be able to rearrange that equation if you need to solve for frequency or lambda given the other two variables. Okay. So that's 8.4. And the questions to do are up here at the top of the page. All right, so we're going to go on to properties of sound waves. Okay, so properties of sound waves. All right, so the speed of sound, well, first of all, sound is a wave. It needs a medium. It needs air. I don't know if you ever played the game in water where you yell at each other under the water and you try and guess what each other's saying. But sound needs a medium. So if the medium changes, the speed of the sound changes. So the speed of sound changes depending on the temperature. Okay. And you could say pressure, but also density, because that pressure and density kind of go hand in hand, okay? The pressure or density of air, all right? But we only consider one of these factors in the course. We only consider a change in temperature, all right? And we can see this by this equation right here. So this is for the speed of sound in air, all right? So this 331.4 is the units are meters per second. And this is also meters per second. But what this T stands for, this T is the temperature, okay, in degrees Celsius. And so what this is saying is for every degree Celsius that's increased, the speed of sound will actually increase by 0.606 for every increase in temperature. So if the temperature was 0 degrees Celsius, it's a winter day, then the speed of sound is 331.4 meters per second. If it's below 0, it'll be less than 331. It's above 0, it'll be above 331. Okay? Now you might be saying, well, why does temperature affect the speed of sound? Well, the temperature affects what the molecules are doing. So if the temperature increases, the molecules are moving faster. And what happens is, if the molecules are moving faster, then they can transfer the energy faster. And when we're talking energy, we're talking about kinetic energy, because sound is really a specific case of kinetic energy. It's molecules moving. All right. And someone I was actually thinking about this earlier and thinking about how when you do a relay race, okay? I don't know if you've ever done a relay race. You have the baton and you're running towards the person. You try to teach this person to move because if you pass off while this person's moving, it'll be a faster pass off. So you can think about that. At lower temperatures, this person isn't moving. So you can't pass off the baton as fast. It doesn't happen as quickly. So maybe that's one example. Or you can just think of it as molecules moving faster and they can transfer the energy faster. And that's why it affects the temperature. All right. Sorry, and I forgot to say, if you needed to see a solved problem for this, it's on page 393. You can see a solved problem on 393, although the practice questions are on the same page. All right, but essentially you're just substituting in the temperature in degrees Celsius. So I think that's one that hopefully you can do on your own. All right, now we're going to talk about Mach number. All right, and what exactly is the Mach number? Okay, so the Mach number, named after Ernst Mach, because he went very, very, very fast. All right, and if you want to read about him, you can. He's there in the book. And what it is, it's just a ratio. It's a ratio of two speeds, okay? So it's a capital M for Mach, yes, like the razor, but hopefully you're not shaving at the speed of sound. So it's the airspeed, okay, of the object over the local speed of sound. Whoops, local speed of sound. So what it means is, what is the speed of sound wherever the object is going? Now, we just use the speed of sound using the equation, although that equation that we just learned on the previous page does change depending on pressure, but we're just going to use it for all locations. All right. So here it's just a ratio. So what I'm saying is, if the airspeed of the object, okay, so if we say it has a Mach number of 3, it means that the airspeed of the object is going 3 times the speed of sound. It means the object is moving at a speed 3 times the speed of sound. Okay, Mach 2 means twice. Mach 1 means 1, and if it was half a Mach, then you'd be going less than the speed of sound. All right, and there's some practice questions there for you to do. All right, now just be careful, they try and trick you, and they have kilometers per hour and meters per second. This 331.4, so the one we just learned, okay, meters per second, when you add the 0.606 times the temperature, okay? That's the equation you're using, but sometimes they give you the airspeed of the object in kilometers per hour or kilometers per second, so you'll have to double check that, okay? All right, now, speed of sound in different mediums, okay? There is a table on page 395. You don't need to copy that, but I'm just going to show it to you for a second. Here it is. At the top of the page there is air at 20 degrees Celsius. It's 344 meters per second. Air at 0, which we expect to be less, okay? And decreasing to negative 20 degrees Celsius, it is less. But then if you look at glass, steel, water, and wood, specifically maple, those numbers are much higher. And think about that for a second. Why? If we were in class, I'd have you put your ear on the desk and tap on the desk and hear how it sounds different. And what happens is that the molecules or the particles in glass, steel, water, and wood are all much closer together. So therefore, the speed of sound in them is much faster. Think of it like dominoes. If you had the dominoes very, very close together, all right, then when you tip them over, it happened much faster, okay? Whoops. Oh, sorry, guys. Okay, so as density increases, the speed of sound also increases. Okay, so what's the relationship between density and the medium? All right, so as density increases, so does the speed of sound. And it's because the particles are closer together. Particles, molecules. All right. So if at any time a question is referring to something and they didn't give you the speed of sound, you might have to go back to that page and check it out. All right. So now, what about sound intensity? Okay, sound intensity has to do with like how loud, how much energy, how many watts are there? It's actually how much power, okay, there is in a sound. All right, now on page 395, it's actually the same page, but it's on the bottom. There are a whole bunch, there's a table, okay, that gives you a bunch of values. And there are 2 scales. So I'm going to show them to you. All right, here they are. So there's the typical sound intensity. So let's do the threshold of human hearing. This means right when you can hear So hopefully, I don't know if you heard me, but if you can just barely hear a sound, that is the threshold, the beginning of you to hear a sound. So for intensity of that, it is 1 × 10 to the negative 12 watts per meter squared. So watts we know is a unit of power, and meters squared is a unit of area. So essentially, it's how much power per area. But there's also another one right there, just to the right, called sound level in decibels. Decibels, okay? It's named after Alexander Graham Bell, and deci meaning essentially it's a base 10 scale. And you look at those numbers and those like, oh, those look nice. They're not powers of negatives. So essentially, this scale right here is based on human hearing. We're saying 0 is when we start to hear, and then it goes up by, goes up by tens here. And this one, it's a very, very small unit of measure. So we tend to use this one just because the numbers are nicer. And really, that's the only reason that they've come up with a different scale. So what I usually do with you guys is pick out some that are interesting and fill them out on the table. So we can just look at this table, and I can still write out some if you want, but so some things that you might be familiar with. Normal breathing at 1 meter. This bothers me when my daughter kind of breathes in my ear, and she's probably closer than 1 meter though. A typical whisper at 1 meter if you're trying to whisper during class and I hear you. An empty classroom still has sound because, you know, there's still sounds and there's waves bouncing around. A computer at 1 meter, you're probably used to that by now. A library alarm clock, a vacuum cleaner. So a vacuum cleaner is 70 decibels, and it's 10 to the power negative 5. Now, if you're a math person, I don't know if you can see the relationship here, but every time this changes by a factor of 10, so I come 0 to 10, this also changes by a multiple of 10. Okay, so if I take 10 to the negative 12 and I multiply by 10, the exponent is getting reduced by 1, and so on and so on. So it's actually a logarithmic scale between these two. All right, it's just that this one starts at 0 and this has a different starting point. So if I look here, 10 to the negative 5, a vacuum cleaner, and 10 to the power negative 12, this is a difference of 7 times. Or if you look from 0 to 70, this also has a difference of essentially 70 times. Okay, but here we see it with the exponent, because if I go negative 12 times 10 to the power of 7, I'm going to get 10 to the power negative 5. All right, so that's just some interesting, math there. And if we look over here, we can also see a rock band, a jet, and then we have a threshold of pain, which means your eardrum is just beginning to hurt. All right, so that would be 130 decibels. All right, if you've ever been lucky to see a space shuttle, not me. Okay, or if you've been near a tornado or atomic bomb, hopefully not, possibly a tornado, but there are some other examples. Okay, so you can take a look at those. All right, so how is intensity measured? It's measured in watts per meter squared, which is power per area, but also in decibels or decibels. Okay, and this is capitalized, but when you write it, it's not, but that's just because of Alexander Graham Bell. Okay, if you want to pick out some interesting ones, you can. All right, and then we're going to talk about loudness and distance. And this, I think, is probably pretty common knowledge, but if you have somebody yelling right in your ear, it's going to hurt. If that same person is yelling at the same volume, but they're all the way across the room, it's not going to hurt as much. Okay, so the loudness, okay, or the intensity, it decreases as distance increases. Okay, so this would be an inverse relationship. Okay. All right, and interesting stuff. What range of frequencies can humans hear? Well, All right. We call this, we've heard of ultrasound and infrasonic waves. I don't know if you're ultrasound, right? So we, again, put ourselves in the middle of it and just say, base everything on us. Okay. So we have the audible, not the reading thing, the audible frequencies, that's frequencies for humans. Okay. It's in the range from approximately 20 hertz to 20,000 hertz, or you can think of it as 20 kilohertz. Okay, but some people don't see that K. It's 20 hertz to 20,000 hertz, okay? And above that, we call that ultrasonic. It's above human hearing. Okay, so that means higher than 20,000 hertz. Now, if we were in class, what I would do is I'd have a wave generator. I'd go on to YouTube and find a wave generator and adjust the frequency, and we'd all raise our hands when we can hear or not hear the sounds. Okay, so that's ultrasonic. Then we have infrasonic. Okay, think of something inferior. It's below. Okay, this is below human hearing. Okay, so that's below, whoops, below 20 hertz. And what I like to do now is talk about elephants and giraffes, because just because we can't hear them doesn't mean they're not making a sound, all right? So if you've ever had an ultrasound, they send sound waves, using that, and they put the goop in, pregnant women have them to see the health of the baby. Essentially, it gives a picture of the baby. And infrasonic, the best explanation I can have is there were giraffes and they were in isolation. And so they couldn't see each other. But some giraffes they didn't realize they were making noises. And when one giraffe picked up its head, so did the other ones in isolation. And with a little bit of research, they realized that they were communicating through infrasonic sound waves that we could not hear. So even though we can't hear them, doesn't mean they are not communicating. And that also applies to elephants, infrasonic. And then we know that dolphins, bats, there are other types of animals that use sound to see, essentially. All right, so there are a couple other questions there to do. All right, and that is the lesson for today. Hopefully you're excited about videos again. Okay, and then you can always ask me questions if you need to. Bye-bye.